This video is part of the MCAT Chemistry video course. Subscribe and hit the bell if you'd like notifications about the release of new videos, and visit ancientbrainstutoring.com for questions about one-on-one virtual MCAT tutoring. In this video, we'll look at redox reactions and go over assigning oxidation numbers in reactions and breaking it down into half reactions and then balancing the reaction. What we're going to look at now is doing redox reaction problems whenever you're not given the structure of a molecule. In the last video, we looked at how you do these whenever you have the structure. Now we're just working with the molecular formula. What you want to do in these situations is look for changes in oxidation numbers, which means we're going to have to assign oxidation numbers to all of the atoms in this reaction. Pull up that list of rules from the last video and just follow along and make sure you're assigning all these numbers correctly. So first, whenever there's no charge, that means all the oxidation numbers have to add up to 0. The next rule that would apply to this first molecule is that oxygen gets a -2. So since there's 3 oxygens total, they would give us -6. So now our 2 chromiums are going to have to offset that -6, which means that each one would be a +3. Now for aluminum, there's no charge on that, so the aluminum gets a 0. For the next molecule, again, our oxidation number should add up to 0. The next rule that gets applied is oxygen getting a -2. There are 3 oxygens, so total that's -6. So our 2 aluminums are going to have to offset that -6, which means each aluminum will need to be +3. And then the chromium on the right is just by itself, and there's no charge, so that gets a 0. Now we need to look at which molecule is getting reduced and which molecule is getting oxidized, and then split this in to the oxidation and reduction half reactions. So first, let's do the reduction half reaction. So find the atom whose oxidation number has decreased, because whenever something has a lower oxidation number, that means that it's more reduced. So we're looking for which atom got reduced. And you can see that chromium goes from +3 to 0. So that means that the reduction half reaction would have to be the molecule that got reduced, which is the chromium oxide, turning into just the chromium that is by itself. So then the oxidation should just be whatever's left, but let's double check that. The aluminum goes from 0 to +3, so then our oxidation half reaction is aluminum going into the aluminum oxide molecule. We're going to stop here at just splitting this up into its half reactions, because balancing a reaction of this level is actually probably out of scope for the MCAT. It's possible that it could come up, but it's extremely unlikely that you would get one this complicated. This next part will look at balancing half reactions that are way more likely to come up on the test, and these are way easier to balance. So for this first reaction here, the only reason I put this is because this is an example of one that you would not need to be able to balance. So if you see something like this where it's looking like it's going to be pretty difficult, do not worry about learning how to balance reactions like this. It's very unlikely that this will come up on the test. The reaction below it is one that you do want to understand, and you do need to know how to balance reactions like this, and it's much, much easier. So start the exact same way and identify your oxidation numbers so you can determine which one got reduced and which one got oxidized. The way that we balance this is by first writing the half reactions. So the reduction is whatever atom lowered an oxidation number. So that would be silver going to silver without a charge. And then the oxidation would be copper going to copper with a charge. Now for each of those reactions, you need to put electrons on one side of the arrow to make the charge on each side equal. So if we look at the reduction part, we have a 0 charge on the right and a +1 charge on the left. So if we're going to add electrons, that's the only way that we can balance out the charges. That means that we have to have an electron on the left side. So silver plus 1 electron will lead to a total of a 0 charge on that left side. For the reaction on the bottom, we have a 0 charge on the left for the oxidation reaction, and then a +2 charge on the right side of that arrow. So that means we need 2 electrons on the right side of that arrow to make the charge on the right side also equal to 0. So we've added our electrons, we've balanced our charges for the redox and the oxidation reactions, and what we need to do now is make sure that the number of electrons on the reduction reaction and the number of electrons in the oxidation half reaction are equal. So notice how the oxidation reaction right now has 2 electrons, but the reduction reaction only has 1 electron. And what you do now is multiply your reduction and your oxidation half reactions by numbers that will make the electrons equal. So if we just multiply the top half reaction by 2, that will give us 2 electrons. And we don't have to multiply the oxidation reaction by anything, because just multiplying the reduction reaction by 2 will get us even numbers of electrons. So that means that our top reaction becomes 2 silver plus 2 electrons gives you 2 reduced silvers. And I'm going to zoom out to complete the rest of this reaction. At this point, we have even numbers of electrons. Our charges on either side of our reactions are balanced. So now all we need to do is combine the reactions. And we are combining this reaction and this reaction. And all you want to do is take everything that's on the left side of both of those reaction arrows and then put them on the left side for our final reaction. So for our reduction reaction, on the left side, we have 2 silver plus, we have 2 electrons, and then we have 1 copper from the oxidation reaction. On the right side of our reactions, we have 2 silver that's been reduced, 1 copper 2 plus, and 2 electrons. If something shows up on both sides of the reaction, then it cancels each other out. So there are 2 electrons on the left side, and there are 2 electrons on the right side, so those will cancel each other out. Notice how we do have silver on both sides, but if you have silver plus, that does not cancel out silver that is uncharged because those are 2 different species. So only the electrons cancel each other out, and we end up with a final reaction of 2 silver plus copper will give us 2 reduced silvers plus copper 2 plus. And again, these types of redox reactions you do need to be able to balance.